simple substitution integration, like integration of a linear term or integration by limits to calculate area under the curve. So we'll continue from that point onwards today. So let's begin. So in indefinite integration, we had not only understood all the formula and a few of the properties, but we had also understood a simple method of substitution. So as part of that, we had understood substitution of a linear term. For example, we've seen that integration of, let's say, e raised power 2x plus 1. This directly becomes e raised power 2x plus 1 divided by 2 plus c, because we had the general formula that if integration of fx is ix, which is the antiderivative, then integration of f of ax plus b with respect to x comes out to be indefinite integration of ax plus b divided by e plus c. I mean, the c is not required, it's part of the indefinite function. So that's how, and this had come by substitution. So we had come from this to this by substituting the linear term as a demi variable z. So dz became this, and by substituting these things we got this. Okay, so how, for example, we would do the substitution in this case if we are doing it by substitution? We would have to substitute 2x plus 1 as our dummy variable. So that means dz by dx would be 2. So we'd be able to substitute dx as dz by 2. So this thing and this thing would be substituted in the integral, and the above integral would then reduce to something simpler. So e raised power 2x plus 1 dx would reduce to e raised power z, but dx is replaced with dz by 2. And this would further be e raised power z whole divided by 2 plus c. And then we would do the resubstitution step. And on completing the resubstitution, this would come out to be e raised power 2x plus 1 by 2 plus c. Okay. And obviously, once you complete the indefinite integration, you can always cross check or double check that you got the antiderivative correctly by differentiating the antiderivative and verifying that you get the quantity that you are integrating in the first place, right? So hope this direct formula and its application in this particular question, and also the substitution method, all this is clear to all of you. Just go through this carefully step by step. Let me know if there's any doubt. We'll discuss. Okay. Otherwise, we'll do a few more examples of this and then move on to the next type of substitution. Okay, so very good. I'm assuming all of you are clear with this. Okay. Now moving on to the next aspect, or before we move on to the next aspect rather, let's do practice of few integrals. Yes. So once you are familiar with the direct formula application, you don't have to do the substitution steps every time, Rishi. Like the direct formula here. So initially how I had just directly written the integration. I know integration of e raised power x is e raised power x. So integration of e raised power a linear term will become e raised power that linear term divided by the coefficient of x, which is 2 plus c. So this formula is made of use of directly. Okay. So that is what we have to get used to doing to apply the formula directly. Okay, so let's look at some examples. So now you work these out yourself. Okay. So integration of cos 2x, integration of 1 upon square root of 3x plus 2. Okay. So just try this out. Yes, Manav, that's correct. Very good. Yes, correct. Nandita, check your answer. Beta. Do it by substitution if required. Instead of using the formula directly, you can do it by substitution also. Yes, Jivitesh, that's correct. Yes, Sai, that's correct now. Rishi, correct. Good. Parth, correct. Aryan, correct. So I'm just writing down the answers of the first two parts. Those of you have already sent me the answers of the two parts and they're correct. Just try out the C and D part. So in this, we are making use of the fact that integration of cos x is sin x. Okay. So integration of cos of ax plus b becomes sine of ax plus b by a plus. Okay. Similarly, this one will become now integration of root x is 2 by 3 x to the power 3 by 2. So this will become, oh sorry, it's not root x, it's 1 by root x. So this is correct on its own, but what we are using here is different. We're using here is this, that is this. So this will become 2 by 3 into 3x plus 2 to the power half. Yes. Or whatever, you can also write it as it's the same thing. Okay. Now similarly in the third one, make use of the integration dx upon x square is minus 1 by x plus. And fourth one, make use of the integration that root x dx is 2 by 3 x to the power 3 by 2. Yes. Yes, Aryan, it's correct now, the C part. Yes, Parv and Manav correct. So this one will become minus 1 upon x plus 2 plus c. And this one will become 2 upon 30 or 1 by 15. Yeah, obviously. So you just simplify it to 1 by 15. So this can, for example, be simplified further also. It can be written as 10x plus 2 into 10x plus 2 to the power half. Can be written like this, or like this, or like this, or like this. They're all okay. Okay, so hope these are clear by these methods to all of you. Okay. So basically, they are just an extension of the basic formula that, as you know, this one comes from the fact that integration of x to the power half is x to the power half plus 1 upon half plus 1 plus c. So that's how we get to this step. And then from this, we can also see that integration of square root of a linear term will become 2 by 3a times that linear term to the power 3 by 2 plus. Okay. Similarly, this one comes from the fact that this is integration of x to the power minus 2. So that is equal to this, okay, which gives you this. So therefore, integration of 1 upon some linear term square will become this. Similarly, this one. Okay. So these all integrations are direct applications of this. Now we come to two very important integrations of trigonometric terms. So for that, we make use of this identity. Yes, Jitesh, you have a question?
No, sir.
Oh. So the identity is that cos 2 theta is cos square theta minus sine square theta, or 2 cos square theta minus 1, or that's the same thing as 1 minus 2 sine square theta. So using this set of identities, we can invert these and therefore write that cos square theta can be expressed as 1 plus cos 2 theta by 2. And using this, we can see that sine square theta can be written as 1 minus cos 2 theta, whole thing divided by 2. So now this and this become very useful identities. Sorry, there's no integration here. Why I wrote the integration sign? We're going to make use of it in integration next, but as of now. So these two are important identities that we can use in integration. Okay. So using this identity, we can see that if we have integration of cos square x, we can write that as 1 plus 2x divided by 2. The whole thing's integration, which becomes further this becomes x by 2 plus sine 2x by 4 plus. So this integration is quite easily solved as this using this identity. Okay. Similarly, you'll see we can also solve for sine square theta's sine square x dx's integration using the second identity. Yes. Similarly, we have integration of sine square x. We use this identity that sine square is 1 minus cos 2 x whole thing divided by 2. So again, split this up. This time there's a minus sign inside in between. That's all. This becomes x by 2 minus sine 2x whole thing divided by 4 plus c. So these are two important integrations, this one and this one. So remember how to integrate them. Use these identities. Okay, so this is something that you should keep in mind as a technique in integration. Integration of sine square or cos square term is done this way. So there are actually a whole lot of techniques like this in integration, but all of them we won't be studying in basic calculus. Most of them you will be studying in advanced calculus in class 12 maths. We will be studying a few of them over here, which we require for our physics applications. So now coming to another type of substitution. Substitution of a function instead of a linear term. So basically the idea here is, suppose we have integration of a composite function multiplied by the derivative of the inner function. So for example, suppose I have integration of square root of 1 plus x square, the whole thing into 2x dx. Okay. So you can see that this square root of 1 plus x square, in this you can take 1 plus x square as g, and you can take square root as f. So f of gx is square root of gx, which is square root of 1 plus x square. You can see that if we have taken this as g, then g prime x is differentiation of 1 plus x square, which is 2x. Okay. So for example, if we have a situation like this, then we use this technique. So we substitute gx as a dummy variable. So on doing that, dz by dx becomes differentiation of gx with respect to x, which is nothing but derivative of g. So now next step we can see that if we cross multiply, then g prime x into dx this whole term is over here. Okay. And this term is getting substituted as this. So doing both these substitutions, our integration becomes a simple integration now instead of, okay. So integration f of gx into derivative of g into dx. So f of gx becomes f of z, and g prime x into dx just becomes dz. So this is iz, okay, where let's say I is the antiderivative of f. So that becomes I of, now z will have to be replaced with gx plus, I mean c is part of the I, so don't need to write. So this is how, okay. So now we can see therefore that the integration of this type of function, composite function, multiplied by the derivative of the inner function in the composite function, that becomes the indefinite integration of f. So antiderivative of gx, that becomes our findings. Okay. So just note down this process, and then we will apply this to this example and more examples also. This example was just to understand that this kind of thing is happening over here, that this is an f of gx kind of term. So because this is a g prime dx kind of term. So this integration is of this type. Now we'll apply this method here to this example also and understand this.
So
Yes.
in the example question, is it 2x dx?
What is the antiderivative beta you said?
Sir, in the example question, is that 2x dx?
Just a minute, I'll just check and tell you.
Sir, on the screen.
This one, yeah, it's square root of 1 plus x square into 2x dx. Yes, that term is 2x dx.
Okay, sir.
Okay. So that's why you can see that 2x dx term is a g prime x dx term, because you're taking g as 1 plus x square.
Yes.
Right? Okay. So if you've written down this method, now try to apply this method of substitution to this question, which is written on the right hand side, that square root of 1 plus x square whole thing into 2x dx. Remember that 2x is not inside the square root, which is why I've written it separately with a bracket. Okay, so let's see how to deal with this particular example. Okay, so in this type of integration, it's not always going to be easy to work it out directly as a formula. We have to do the steps typically. So let's look at the example I give you. So I'm just rewriting it in a different way. But it's the same question. Okay. So now in this, what we have to identify first of all that square root of 1 plus x square is a composite function. Okay, this is a composite function. Okay, where gx is 1 plus x square and f of gx is basically square root of gx. So therefore square root of 1 plus x square. So f is the square root function. Now the other thing you also identify along with this, that 2x is the derivative of 1 plus x square. That means this is gx, then g prime x is equal to 2x. Okay. So therefore the integration is of this type. It is of the type where we know what is gx. Gx is 1 plus x square and f is the square root function. Therefore g prime x is 2x and so on. So the first thing is to be able to identify that this thing is happening in this particular integration. That the term inside the integration symbol, it is a product of two things. One is a composite function and the other thing is the derivative of the inside function gx. So it's the product of 2x into square root of 1 plus x square, where square root of 1 plus x square is a composite function for which the inner function is 1 plus x square and 2x is the derivative of that. Once you identified that, then you can apply the method. So once you have identified, now we will apply the substitution method. So for that substitution method, in this integration of 1 plus x square, now I'm again writing this in the other order like this. It doesn't matter, it's the product of two things. Okay. Substitute 1 plus x square as g, something we've already seen above. Okay. So square root of 1 plus x square becomes, oh sorry, we have to substitute this as z. Right. So that is now our dummy variable. Substitute 1 plus x square as z. This is our dummy. So square root of 1 plus x square becomes simply root z or z to the power half. Okay. And more importantly, dz by dx is 2x. That means when we cross multiply, 2x into dx can be substituted as dz. So this is the two things we'll substitute. We'll substitute this as this and we'll substitute this thing as this. So the integral will now become simple to solve. So as you can see, the integration now has become z to the power half into dz, which is a direct integral, z to the power 3 by 2 divided by 3 by 2 plus c, or 2 by 3 z to the power 3 by 2 plus c. Now we resubstitute. So integral becomes 2 by 3, z was 1 plus x square to the power 3 by 2 plus c. So that becomes my answer. Okay, so it might still seem that it's a bit lengthy, but you will realize with practice that it's not lengthy. The tricky thing is to be able to identify whether or not we can use this substitution, because when we can use this substitution, only when this condition is satisfied, that the quantity we are integrating is the product of two terms. One is the composite function f of gx and the other is the derivative of the inner term, that is g prime x. Okay. So once this is happening, you can see that this is of this type. So this is the thing that is important to be able to identify. Then after that, the steps are easy. So I'll just take you through this step by step again. You can make a note of the key points here so that. So don't worry, we'll do practice of more questions of this, but currently just make sure you understand all the steps in this particular question. Integration of 2x into square root of 1 plus x square. Okay, so people, hope the steps, now just go through this once. Hope these steps are clear. Parv, to answer your question, no, there is no direct equivalent of product rule or quotient rule. There is another method of integration apart from substitution called integration by parts, but that also you'll be doing in advanced calculus. For us, calculus, I mean, integration will end over here in basic calculus with substitution. And substitution is a sort of an equivalent of chain rule in differentiation. So now, after you complete this particular integration and all the steps, now try out these next few.
So we are just learning till addition and subtraction.
Oh, till substitution, integration by substitution.
Yeah.
Properties we have done earlier, and integration by substitution, that's the thing. Okay, so just try out these. Okay, people, I'm waiting for your answers.
Sir, I've given the answer in chat.
Okay. Wait, I'll check who all are correct. Yes, Jitesh correct for the first one. Rishi correct. Manav correct. Very good. Yash, you have to check your answer for the first one. Okay. There is a square root now, so it will not come in ln terms. Okay. Okay, Parv correct for the second one. First one, check your answer. Muskan correct. Very good. Jitesh correct for the second one. Manav correct. Okay, so people, let's work out all these questions. I've got a lot of people sending me the answer. We will check it out. Okay. So as you can see in the first one, let's go step by step with each one of these. So in the first one, you can identify that if you take 1 upon root sine x as your f of gx, okay, then your gx is sine x, right? And your f is power minus half. Okay. And then your cos x is g prime x. So this is the critical step. See, whatever you take your gx, your g prime should be there in the integral. Okay. So therefore, I can substitute. So I'll substitute sine x as z. So dz by dx is cos x, or in other words, cos x dx will become dz. So this thing we can easily substitute, and of course, this thing we can substitute. Okay. So completing the substitutions, the integration becomes dz upon root z, or this. So z to the power minus half plus 1 upon minus half plus 1 plus c. So that is 2 root z plus c, which after resubstitution will become 2 times root sine x plus c. Okay. And just as a verification process, let's verify that this is the antiderivative. So if you differentiate this, what you will get? See, take the 2 outside, then 1 by 2 sine x to the power minus half into derivative of cos x, we'll get this. So that is cos x by root sine x. And that is the function we were integrating. So this is correct. So that means this is the antiderivative. This quantity is the antiderivative of cos x upon root sine x. Okay. So just note down the steps if necessary. If you've done it, it's fine. Try out the fourth question or third question, whichever question you are at. And I'll discuss the second one. Okay, so if it takes you time to figure out a question like this, don't worry too much. This is a more tricky part of the application of integration. And I mean, believe me, if you're just clear with the methods, you will not have difficulty at a physics level. For maths in 12th, you'll have to practice a lot, at least 5-6 times what we are doing right now over here. But the good thing is, whatever we are doing in physics here, that will be a good foundation for you for your class 12th advanced calculus portion in maths. Okay, now let's come to the second one. So this is also quite straightforward. You can directly see that 3x square is the derivative of the term which is on the power of e in the exponential function. So immediately you can understand that you can identify quite easily that in this function, okay, you can identify that this term is g prime x, provided we take this term as gx. Okay. So that way you can now see that you substitute that gx term x square plus 2 as z. So dz by dx is 3x square. So 3x square into dx becomes dz. Okay. So this integral we can write like this into 3x squared dz. So into 3x squared dx. So this whole term will now become dz because this term we have put as z. The integral has just become e raised power z. So quite easily that is. Let's put this down. Okay, so this is done. Let's come to the next one. So let me see how many of you got the fourth one correct. Okay, good. Yeah, but the thing is, if you can identify it directly, you can do it directly, but chances of making a mistake are more. For example, in the exponential one, you could have done it directly. You could have seen this will be e raised power z dz, so it's fine. But for example, in this cos x by root sin x, it's a little tricky to do it directly. Okay. So I would say at least at this stage, avoid doing it directly. Whereas the linear substitution ones you can do directly. The ones we have seen before this method. Linear substitution ones you can go for directly. Here, just write down the couple of steps that are required. Doesn't take that much time. Okay. So again, in this one, you can identify that if you take this term as your z, then this term is dz by dx. Okay, so substitute. So see, once you get used to this, then you can skip one step. You can write it directly as integration dz by root z and go that way. Okay, but absolutely directly is a bit tricky. Okay, so substitute x square plus x plus 2 as z, 2x plus 1, or in other words, 2x plus 1 dx is equal to dz. So this and this, we'll substitute these two terms. So the integration will become dz by root z, okay, which you know is 2 root z plus c, correct? So that will become, after the substitution, so that is the indefinite integration. Okay, simple enough. Uh, okay, there's actually the dummy variable is not meant to confuse you. It's actually meant to make the process simple and straightforward. Okay, so I would just suggest that get used to that concept of substituting a variable and therefore transforming the integral. Or in the case of differentiation also, sometimes you will see that you can have a situation where it's necessary to do the substitution step. You can't do the calculation directly in your mind always. Okay, so, and here in physics is okay, you won't have such complicated questions. But especially when you come to your advanced calculus in maths in 12th, okay, you will need to know each and every method inside out. Okay, you can't skip one method over the other because you never know what kind of tricky question you can get. So just get used to the concept of dummy variable with a bit of practice. Okay. I have demonstrated most of the questions both from chain rule in differentiation as well as integration by substitution with a proper explanation of the substitution step. Okay, without doing any direct guesswork kind of thing.
Sir, so
So
like
if you
what
just
I
go
meant,
through my notes and go through those questions and each and every step again, I think you will get used to it. Okay. So now again, you can see that if you take this as a variable z, one is a constant, so it will not matter. So sec square is the derivative of z. So that's it. That's the substitution. Take 1 plus tan x as z. So dz by dx is sec square x. That means sec square x dx is dz. So this and this we substitute. So the integration becomes dz by z this time. So that is natural log of z plus c. Remember, this is the exception. Okay. So not to forget this thing that in general, this is x to the power n plus 1 upon n plus 1 plus c. But with the exception that, okay, the exception case, always remember, it's natural log case. Okay, so that's that. Okay.
sir, so like
Yes.
what I meant was in differentiation, like
Hmm.
there was one step where we substituted a certain thing as z and then we did dz by dx in the chain rule. So
Yeah.
like we did it that way, like dy by dz into dz by dx. So like instead of just putting z, I I just used to put the whole thing in there. So because sometimes that substituting as dummy variable and then resubstituting it back.
Yeah, I mean, you can do, but the thing is, see, in extremely lengthy questions, na, there is a chance that you will, because see, when you are skipping writing that Z, basically you are doing one bit of calculation in your mind without writing it down. It's nothing more than that actually. It is like, just skipping one step and doing that direct calculation in your mind. So it's fine, but if things get very lengthy, then there's a chance of confusing something in your mind and making a mistake. So actually writing the dummy variable is a more systematic method. It's longer, but it's more systematic. So that's why I'm just asking that if you try, you can get used to the method of dummy variable.
Okay, sir.
Okay, now let's see two interesting examples of this where it actually shows how to derive a direct formula. So remember I told you that when we did integration of tan x dx as ln sec x, okay, so I had shown you then that if you differentiate this, you'll get this, and that was the logic of it. But how to derive it? So let's look at the derivation of this. So the derivation actually comes from substitution. Integration of tan x is sin x by cos x. Okay. Now that cos x is derivative is minus sin x. Okay. So that means if we substitute z as cos x, okay, then sin x dx that we have in the numerator will become minus dz. Okay, because okay, so let's reverse. So now substituting these two, so integral tan x will become minus of dz by z. That minus sign is just a minus one constant kind of thing. So we bring it outside. Okay. So it becomes minus ln z plus c. So further, that becomes minus of ln cos x plus c. Now use the property of ln that any coefficient outside comes inside as a power. So this becomes ln of sec x plus, because you know the property of log. This is, so therefore minus of ln x is ln x to the power minus 1 or ln 1 by x. So that's the property we've used. So you can use this, okay, to also uh, similarly you can prove this also. Integral of cot x is minus ln cosec x plus c, or you can also write it as ln sin x plus c. Okay, so Rishi, hope this question is clear now in the end.
Yes, sir.
Okay, now the other two are little bit more, we use a trick. Integration of sec x, for example. You can't directly write it as 1 by cos x, it will not lead to anything. But we just use a trick here that you multiply and divide it by sec x plus tan x. And then what you observe that it becomes sec square x plus sec x tan x in the numerator divided by sec x plus tan x in the denominator. And now it's a matter of observation that if you take this as z, then this whole term here, this is dz by dx. So therefore, you substitute z as sec x plus tan x. You can substitute sec square x. Actually, if you differentiate, this will come in the reverse order. Differentiation of sec x is sec x tan x. It doesn't matter. Okay, and differentiation of tan x is sec square x. So this into dx will be dz. So your integration will become dz by z, which is ln z plus c, or that is ln of sec x plus tan x plus. So there's still manipulation involved here. Before we are doing this is the substitution step. But before doing the substitution, we are doing a manipulation. So, but anyhow, if you want to understand how this is derived directly, this is how this is done. Now, one more thing we have to keep in mind, that suppose we have something like this. Okay. Again, a bit of manipulation. Now you can see that if you take 1 plus x square as z, then dz by dx is 2x. Now we don't have a 2 in the numerator. Okay. So we'll have to adapt this a little. So we'll have to adapt it in such a way that we'll understand that dz by 2 is becoming x dx. So we have to substitute this. There will be an extra half term. Okay, and we'll substitute this. So doing that, our integration x dx upon 1 plus x square will become dz by 2 divided by z, or 1 by 2 dz by z plus c. So that is 1 by 2 ln z plus c. And one more step here, that 1 by 2 can be taken inside. So it's ln of z to the power half. So it is ln of square root of, now z was how much? 1 plus x square. Yes. So this integral is finally becoming like this. Whereas had there been a 2 in the numerator from before, it would have been ln of 1 plus x square.
So would you just scroll 1 second up? I wanted to
Scroll up. Okay, just a second.
that lock part.
Yeah.
That's what.
This second one, right?
No, a little up.
Acha, that property of log.
Yes.
Yeah.
Okay, sir. Thank you.
Okay, done now. Okay, just coming to the next thing now. Right. So with these techniques in integration by substitution, okay, you'll be able to handle all types of integrations that you'll come across in physics at least. Okay. There are more complicated integrations also and few more tricks and methods. But as I said, all those things you will look at in advanced calculus and maths. Okay. And you can go ahead and start studying advanced calculus if you feel like it. There's nothing like it. But I think given your workload in all three subjects, you should go according to the logical sequence that we are following over here. And if after completing everything you have extra time, you can always, depending on whatever is your interest in your subjects, you can do some extra reading and go ahead also. Anyhow, now let's come back to integration, definite integration and area under the curve from it. So this was the second type of operation in integration which we had seen. So it's seen that in this, the integration sign comes with another two quantities here. Okay. And those are called the limits. So we write it as either like this, or sometimes we also write it as x equal to a to x equal to b. They mean one and the same thing. So here b is what we call the upper limit for the variable x of integration, and a is what we call the lower limit for x. And this quantity actually gives us the area under the graph of y is equal to fx between the limits x equal to a and x equal to b. So this has a geometrical interpretation. Antiderivative doesn't really have a geometrical interpretation. Antiderivative is a simple thing that we are trying to find out a function which is the antiderivative for the given function fx, such that if we differentiate that function, we will get the original function fx. That's all. Okay. But here, this one has a geometrical meaning. So if this is, let's say, the graph of this function, and these are the limits a and b, then the area subtended by the graph, or the area enclosed by the graph between these two limits, this area is what we are talking about over here. So this is the area that this calculates. Now, how to do the calculation? That comes by substituting. If the indefinite integration gives us the antiderivative ix, then the definite integration from a to b is given by the value of the antiderivative at b, that is the upper limit, minus the value at the lower limit. Okay. So as we had seen as an example, suppose we are integrating x cube plus 2x, let's say, from x equal to 1 to x equal to 2. So what we have to understand is that the antiderivative of this function is what? It's x to the power 4 by 4 plus x square, okay, plus c. But on this antiderivative now, we can put the limits 1 to 2. So it will become the value of the antiderivative at the upper limit. So that is going to be 2 to the power 4 divided by 4 plus 2 square minus 1 by 4 plus 1 plus c. Okay. So that's becoming 4 plus 4. Okay, c will cancel out, minus 5 by 4. So that is 8 minus 5 by 4. So that is 32 minus 5, that's 27 by 4. So this becomes our answer. Okay. This is the value of this integral. So sometimes we just introduce an intermediate step, that when we're doing a to b fx dx, we first write it as the antiderivative, but on that we put the limits. So that becomes the value of antiderivative at b minus the value of antiderivative at e. So you can see this quantity here, this is nothing but I of b, and this quantity here is nothing but I of a, and the constant of integration cancels out. Okay, so that's why we get a definite numerical answer. It's not a variable, it's not a function in terms of x, it's a numerical definite answer, and that numerical definite value is nothing but the area enclosed over here. So you have seen this part earlier, but just make a note of this new example that we're doing. Okay, and then we will pick up one or two more examples.
Sir, is that mod?
Sorry? Oh no,
Is
oh,
that
okay, that
mod?
bar is not mod actually. Actually, there should be a single bar, so that you don't confuse it with mod.
Yes.
It is just a way of writing it so that we are going to place the limits on the indefinite function. Okay, so we don't need to put two bars here. We just, rather you put this antiderivative in a bracket and then put this bar here with this. So this shows basically that this is our antiderivative, but we are going to put the limits. We are going to apply the limits to this now. So it will give us the value I at upper limit minus I at lower limit. And this is going to be the final answer. This is going to be our area. So that is that 27 by 4.
Yes.
Okay, so now let's look at an example of this, which will also give us an interesting property of this. So we will do integration of sine x from 0 to pi by 2 first. Okay. Then we will also do integration of sine x but this time from minus pi by 2 to pi by 2. And we will follow that up with integration of cos x, again from 0 to pi by 2, and again cos x, but from minus pi by 2 to pi by 2. So once you get the idea of what to do here, just calculate try and work out one of the integrals yourself. You'll see the others follow a similar kind of pattern. Should be quite easy and fast for you to work it out. Yeah, finish writing down the above part, then you can come back to this. Okay, I'm going through your answers. So Aryan, very good. Your answers are all correct. A, B, C, D. Rishi, correct. Jitesh, check your answer for the second one and third one actually. Muskan, correct. Very good. All four are correct. Jitesh, your first one is correct. Something went wrong with the second one. Just check it out. Om,
Yes, sir,
correct.
I corrected it.
Yeah. Om, correct. Rishi, correct. Manav, correct. Muskan, correct. Jitesh, the third one is correct now. And second is also correct. Good. Parv, you have to check your answer. Arya, correct. And Aryan also correct. Okay. So basically, you have to just use two simple integrations over here. One is that integration of sine x is minus cos x, remember? And integration of cos x is sine x. Now, on this, you have to just put the limits according to what the question has given. Okay, so as you can see, for the first part, integration of sine x from 0 to pi by 2. So the indefinite integration is minus cos x. On that, we'll put the limits x equal to 0 to x equal to pi by 2. It doesn't matter whether we write x equal to in the limits or not. We can just write 0 to pi by 2 also. So anyhow, the upper limit will become minus cos pi by 2. You can leave out the c because anyway it will cancel out. And the lower limit will be minus cos 0. So as you can see, this is 0 minus of minus 1. So it's becoming 1. Also see what it is showing us in terms of the geometrical interpretation. So by now we are all very familiar with the sine and cos graph. So sine graph, basically it looks something like this one. Looks like this. It's not a very well drawn graph, but anyhow, we'll try to do a better job of it. So this is our sine graph. Somewhere here will be our y-axis. So anyhow, so this point is pi by 2. And this point is minus pi by 2. So the first one is this area. And that is why the second one, interestingly, will come out to be 0, because any area that is below the x-axis will be considered with a negative sign. So what will happen is that you're taking the algebraic sum of this area and this area and the second one. When we are taking the limits from minus pi by 2 to plus pi by 2, it comes out to be 0 because of that. So what happens here is you can see that the area from minus pi by 2 to 0, that area is actually minus 1. And then from pi by 2 to, 0 to pi by 2, that's plus 1. So that is why the total area from minus pi by 2 to pi by 2, that comes out to be 0. So it's basically the algebraic sum of the area above the x-axis and the area below the x-axis, okay, which is what your calculation will also show you. This time it is minus cos pi by 2 minus of minus cos minus 1 by 2. It's 0. Something went wrong here. It's got rubbed, I think. So rewrite it. This is 0 minus of minus 1. That's 1. Now, the other thing that this graph will show us is that cos x and sin x graph are very similar in shape. It is just that they are displaced. Okay. So we'll see this other very interesting aspect about this, that if you are to compare the graph of cos x with the graph of sin x, there is no difference in the shape actually. It's just that they are like shifted with respect to each other, which is why you have those kind of relations, that cos of x plus pi by 2 is minus sine pi by 2, and sine of x plus pi by 2 is cos pi by 2, those kind of relations. So if this is your sin x graph, I'm only drawing in the positive domain just now. Okay, bring it to the negative domain also. Let's go. So in comparison, the cos x graph is actually like this. It's like the same shape, but it is just shifted. They have this very interesting relationship. This is the cos x graph. This is the sin x graph. So you can see here that this point is pi by 2. This point where they're exactly equal is pi by 4. This point becomes pi. This reaches minus 1. This point is 3 pi by 2. This point is 2 pi. And then this whole cycle repeats. So because of this, it comes as no surprise that integral of sin x from 0 to pi by 2 is exactly equal to integral of cos x from 0 to pi by 2. And they are both equal to unity, because if you individually look at them, the sin x graph between 0 and pi by 2 is like this. Whereas the cos x graph is like this. But these two areas are same because they're symmetrical. And this will be equal to, for example, sin x from pi by 2 to pi, because that will be now this area. This side and this side will be the same. Okay. But for example, integral of cos x from minus pi by 2 to pi to 0 is also 1, because cos x is like this. Okay. So that is why your D part's answer comes out to be 2. Okay. And your C part's answer comes out to be 1 again. So a lot of interesting aspects of the symmetry of sine and cos graphs can be understood by this area under the curve and integration also. Yes, so area under the curve will come negative also for certain. So for example, if you look at sin x dx from, let's say, pi to 3 pi by 2. If you do this calculation, you will see it will come out to be negative. And if you look in the graph also, you'll understand why it comes out to be negative. It's minus cos of 3 pi by 2. Okay. Minus of minus cos pi. So it's easy to get confused here, but this is minus of minus 1. So it comes out to be minus 1. And you can understand why it's coming out to be negative, because sine graph goes like this. So this is the negative area we're talking about. This area is minus 1. Okay, so but this is clear now. So both the mathematics, I mean the integration calculation is also showing us that it can come with a negative sign. And graphically also you can see that the area enclosed can be a negative value because it's falling on the negative side of y. So like when we consider algebraic quantities, it's like, if we have a rectangular thing like this, we'll write that area as length into width. Okay, but if I have a rectangle which is like this, and it's an algebraic quantity, so then this quantity will be taken as minus L, whereas this is B. So this one's area will become minus of L into B. So that's how we can understand that area can be interpreted as a negative quantity also. Because here x and y are quantities we are considering with algebraic sign. So okay, people, so with this we complete integration actually. So we have come to the point where we are done with our first at least all the concepts. Okay, maybe one more lecture we will devote to doing some questions and maybe clearing some of your doubts and discussions and things. Okay, but we are done with calculus now, and we are poised to begin with the next chapter, which will be like a proper physics chapter. Kinematics is the next chapter that we will do in this track. Kinematics is the study of motion. Okay, so we'll start straight away with motion along a straight line. Then we'll move on to motion in 2 dimensions and 3 dimensions, which will then start involving vectors also. So particularly component algebra of vectors that we have learned, and in relation to that, addition and subtraction and those kind of operations will be important in kinematics. Whereas other operations like dot product and cross product, they will become significant in further future chapters of physics, not so much in kinematics. Okay. So make sure you keep in touch with your vectors concepts as well as calculus, because both will be needed straight away from kinematics onwards. So that's it for today's session, people. Now you have to look to complete the module exercises for integration. Okay, whatever questions are remaining which are of integration. Differentiation, I hope you have completed all the module questions by now. As part of your preparation of the MT2 only you would have done. However, if anything is pending, we will keep some time aside in the next lecture also for discussion of questions. So that's it for today's session, people. Wish you all the best. Thanks for attending. Have a nice day.
So,
Yes.
so kinematics contains motion, right?
Kinematics is motion only. The name kinematics was only like its translation is motion.
So,
It's the
sir,
study of motion.
Hemant sir has started a new chapter, Newton's laws of motion. So, are they?
So that is dynamics, beta. That is to do with force. So it is like that is the cause of motion. It's like force creates acceleration, and acceleration creates the motion. Whereas in kinematics, we'll study, okay, we know the acceleration, then what we can say about the motion, how the object is moving, what is its path, what is its distance, displacement, those kind of things.
Okay, sir. Got it. Thank you, sir. Bye, sir.
Okay. Yeah, Parv, you have a doubt, beta?
Yes, sir.
Yeah, tell me.
Sir, just like Darsh was confused using that dummy variable. So likewise in differentiation, like in chain rule, we used to do that if the function is like under root x cube plus 1. We used to do that differentiation of under root x cube plus 1 by differentiation of x cube plus 1 into d of x cube plus 1 upon dx. So like without using dummy variable. So sir, likewise in integration can be used.
Yeah, so likewise the direct formula I told you, integration of f of gx into g prime x becomes I of gx.
Yes, sir.
So if you can identify what the functions are, you can do it directly that way.
Okay,
but
sir.
It just takes a little bit more practice, and sometimes it can become a little tricky when the functions are a little big to handle.
Okay, sir.
Understood?
Yes,
sir. Basically,
like when you did chain rule also initially, it was not so easy to directly do the differentiation. It was easier to substitute, use the chain rule and all that. So same thing applies to integration also.
Okay, sir.
Okay, so with practice you'll get used to it.
Sir, so it was like the same thing as the dummy variable. Just instead of z, we just use the entire thing. So suppose z is x cube. then we would just write x cube. So like d of root x cube upon d of x cube, instead of the d of root z upon dz into dz by dx.
You can just directly substitute the whole integration in terms of gx and g prime x that way, and you can do it. Yes, that's correct. Okay.
Sir.
But anyway, what I suggest is like initially at least try out the questions with the proper substitution steps, and then as you get used to it, you can try to do it, work it directly. Okay.
Okay, sir.
Okay, people. So wish you all the best. That's it for today.
Thank you so
Sir,
much.
and I had a doubt in one of the major test questions.
We will keep a session now for the discussion of major test questions and all.
Okay, sir.
There will be a discussion session. You can also send the question to me on WhatsApp. I'll send you a hint. You can try it out again yourself once.
Okay, sir. Thank you.
Anything in physics, whether it's calculus or vectors, you can send it to me. I'll give you a hint. You can try it yourself that way.
Okay, sir.
Okay.
Thank you, sir. Bye, sir.
Bye. Bye.